Okay, so an introduction to rational functions. A rational function can be written of the form f of x equals n of x over d over x. Okay? Well, all they're saying is what? The function is a fraction, ratio, rational number. N and d are polynomials, but d cannot be 0. Well, why can d not be 0? Because we can't divide by 0. That'd be a whole nother error. No 0 in the denominator. Exactly. In general, the domain. What is domain?
X.
Domain is the list of all possible x values. Same thing we've been doing before. We said what? The domain, we always assume it to be all real numbers. But there are two possible problems. You're not allowed to divide by 0. You're not allowed to take the square root of a negative. You think you could have one of those problems here? Yeah, divide by 0 error. So what we have to do then is we're going to have to figure out where does the domain give me problems. In general, the domain of a rational function of x includes all real numbers except the x values that make the denominator 0. Again, what I just said. Much of the discussion of rational functions will focus on their graphical behavior near these x values. So rational functions have very interesting characteristics when they get really close to somewhere they are not defined. So again, where are they not defined? Well, when we divide by 0. So what we're going to do is we're going to focus on what the graph does at these points. Okay, so it's going to start off being very exploratory. So this first thing is not really what you're going to be doing. It's to give you an idea of what is happening. So if we had to find the domain of 1 over x, well, what's the domain? Well, we assume it's all real numbers unless we divide by 0. So what could make me divide by 0 here? Well, if the denominator is 0, that gives me a problem, right? So when x is 0, bad stuff. Graph is funny. So if I was asked for the domain would be from negative infinity up until 0, don't include 0, and it would go from 0 all the way to infinity. All we're doing is taking out that one problem area. So the first part, find the domain. There's nothing new to you there. Now what we want to do is we want to discuss what's the graph going to do when we get close to 0. Okay, because at 0 we know the graph's going to not exist at 0. So what's going to happen when we get close to 0? So let me get a graph here for us to look at. And then let's plug in some values to see what the graph's going to look like. Obviously, we could put it on a graphing calculator, but that's not our purpose here. So let's think here. What are some x values that we could plug in? Well, let's see what happens when we get close to 0 from the negative side, right? As I'm coming from negative infinity to 0, let's see what the graph is doing. So let me see. Let me plug in negative 2. So when my x value is negative 2, what's the y value? Well, think about it. Plug negative 2 in. You would get 1 over negative 2, which is negative a half. So that means negative 2, negative a half is on the graph. So somewhere right here. Okay? Now let's plug in negative 1. We're getting closer to 0. We know 0 is going to be a problem. Now what happens when I plug in negative 1? 1 over negative 1 is negative 1. So negative 1 would be on my graph. Okay? Now let's get closer to 0. So what's the next thing we want to plug in? What if we plugged in negative a half? Well, what is 1 divided by negative a half? You might need your calculator. 1 divided by negative 0.5, but it is negative 2. So at negative a half, the y value should be negative 2. Well, this graph is moving an awful lot to be getting close to 0, right? We know it's not going to exist at 0, but it's looking good. It's looking good. All right, now what else do we plug in? Let's plug in negative a quarter. So negative 0.25. That's even closer to 0. If I plug in negative 0.25, what's the y value going to be? Negative 4. So that's going to be right in here. Okay, all right. And if I get even closer, what if I plugged in negative 0.1? So I'm getting real close to 0. What's the y value? Negative 10, right? So at negative 0.1, that means when I'm just barely here, the y value is all the way down here at negative 10. All right, well, what about at negative 0.01? I'm getting even closer to 0. I'm getting closer, closer, closer. What's the y value going to be here? Well, 1 divided by negative 0.01 is negative 100. If I get even closer, negative 0.001, the y value is negative 1,000. So what's the graph doing as I get closer and closer to 0? It's falling off a cliff, right? It's going extremely down, really fast, the closer it gets. Okay? So we've kind of got a good idea what the graph's doing here, right? The graph is moving in and going in that direction, real fast. Now what's the graph doing at 0? Nothing. It doesn't exist there because 0 is a break in the domain. So 0 is no good. So let's see what happens when I approach the graph from the right side. So same idea, but let's plug in values that are over here, getting closer to 0. So we started with negative 2 before. Let's start with positive 2. Now, oh no, they're tied together. Dang it. Okay, so we'll just have to deal with it. All right, if I plugged in 2, what's the y value going to be? It would be 1/2, right? 1 over 2. So I go to 2, 1/2, and right here my graph would be. Now if I get closer to 0, so if I plug in 1, what's the y value? Well, 1 over 1 is 1, so I have the 0.11 is on my graph. Okay, get even closer to 0. What if I plugged in 1/2? I would get 2. What if I plugged in 1/4? I would get 4. Same thinking. What if I plugged in 0.1? I would get 10. If I plugged in 0.01, I would get 100. If I plugged in 0.001, I would get 1,000. I could keep getting closer and closer and closer, and that y value is going to get higher and higher and higher. So as we approach 0 from the right side, the graph is taking off in this direction. Right? It's getting taller and higher. And the graph's going to level off here. All right, so my graph is basically in 2 pieces. I have what happens left side and on the right side. And this is kind of what that graph looks like. Okay, from the table, note that x approaches 0 from the left. As x approaches 0 from the left, my y values decrease without bound. What does that mean without bound? There's no boundary. There's nowhere that it's going to get to this level and say, all right, you don't go any lower than this. It's going to decrease forever without a boundary, all the way to negative infinity. And then it says, in contrast, as x approaches 0 from the right, the y values increase without boundary. So as we come into 0 from the right, my y values are getting taller and taller and taller, higher and higher and higher. So, we can conclude from this, because it's in mismatched positions. Do you think that there's any point where the graph connects and jumps from here to here? Does it jump all the way from negative infinity up to positive infinity? No, it doesn't. So the graph is not continuous, is the purpose they're wanting us to see there. This graph is not continuous. There's a break in it. And then the graph is shown here from what we have done so far. Here, and then they want you to figure out what is happening near any excluded x values. So first find the domain, and then we want you to plug in some values and see what's happening when you get really close to that problem in our domain. Equals x squared plus 4x plus 3 over x squared plus 2x. Let me change it. I don't want that to be 2x. X squared plus 3x plus 2. Okay? So say this is my rational function. The form that we're looking at right here is what I call general form, where they're written out as polynomials. Okay, so this is the general form of a rational function. Now, you're going to be given a form. You may be given general form or you may be given factored form. Whichever one you're given, the first thing I want you to do is find the other form. So we're going to have two forms on every one of these problems before we ever start working it. So if I'm given general form, then I'm going to have to find factored form. And so what does factored form look like? Well, it's really just where we factor the numerator and we factor the denominator. Sometimes it may be a GCF. Sometimes it may be a difference of squares, difference of cubes, sum of cubes. It may be a trinomial that you have to do A times C. Right? Everything goes back to that first week on that factoring paper. It could be any of those forms. So, whenever I'm wanting to factor this, do I need to do A times C, or can y'all look and factor this without A times C? Do I do A times C for anybody? Hands up if I need to do A times C. Okay, so I can factor that top. I know that that factors to be x plus 3 times x plus 1. Now the denominator, when I factor it, that's going to be x plus 2 times x plus 1. So I have a general form of my polynomial, and I have a factored form of my polynomial. First thing I'm going to do, make sure I have both of them. All right, what are you going to do if it gives you factored form to start with? Distribute and find the general form. Okay, you need both. They both tell us different things about the function, so you have to make sure you have both of them before we begin. The first thing we're going to look for are wholes. Okay? In order to find the wholes, we're going to look at the factored form. Okay, we're looking at the factored form. Any common factors between numerator and denominator create a whole. And I said earlier, a whole is a point. It's not a line. So my answer for a whole is going to be an ordered pair. So when I look at, okay, let me give everybody a chance to copy. Sorry, I get carried away. Do we have any common factors in the numerator and denominator? Yes. x plus 1 is a factor in both the numerator and the denominator. So that tells me there's a hole created in the graph by the factor x plus 1. So I'm going to essentially cancel the x plus 1's out in the numerator and denominator. But when I cancel them, I know there's a hole in my graph at that point. So I'm going to then say, well, x plus 1 creates a hole. So when x is negative 1, I'm going to have a hole in the graph. I'm just solving, right? X plus 1, where does that give me? 0. So x equals negative 1 creates a hole. Now, to find out what the ordered pair is, we're going to plug negative 1 into the reduced factored form. So I've reduced it by canceling out a factor. That means I'm plugging in negative 1 to the reduced one. So I have negative 1 plus 3, which is 2, over negative 1 plus 2, which is 1. So that would be 2 over 1, which is just 2. So that means the hole in my graph occurs at negative 1, 2. So again, just a little note. We want to plug into reduced factored form. Okay? Now, is every problem going to have a hole? No. That only occurs when I have common factors. If you don't have common factors, then when it asks for the holes, you write none. Because there aren't any. That can happen. So don't think I've got to find a hole every time. Because you don't. Any questions about how we found the holes in the graph? Next thing I'm going to look for are the vertical asymptotes. So to find the vertical asymptotes, again, we're going to look at factored form. Looking at the factored form. Any factors in the denominator that don't cancel gives a vertical asymptote. Okay, and we saw this happen yesterday. Remember, we were looking, what breaks my rational function? Well, it was when the denominator became 0. Right? Well, there was no holes in the graph, so we just looked at what happened when we got really, really close to 0. Well, we had that graph doing crazy things in both directions. That's because at 0, we had a vertical asymptote. So here in this problem, I have a common factor. That means this gives a hole. It does not give a vertical asymptote. But this factor that's left, that did not cancel, will give me my vertical asymptote. So I'm going to set the denominator equal to 0. That did not cancel out. So that's going to give me x plus 2 equals 0. When I solve, that means x equals negative 2 is the equation of a vertical line that is an asymptote. So again, it's not just negative 2, it's the entire equation of a line. X equals negative 2. Any questions about finding vertical asymptote? Okay? Can I squish it? Okay? Now the last one, let me just go to a new slide. Okay, the last thing we're going to look at is a horizontal asymptote. And to find the horizontal asymptote, we're going to look at the standard form. Of our rational function. So we don't need the factored form for this one. We need the standard form. So that's why I've only got that one listed. Okay? Now then, what we're going to do is we're going to compare degrees of the numerator and the denominator. Okay? If the degree of numerator is less than the degree of the denominator, then we have a horizontal asymptote at y equals 0. Which means it's at the x-axis, right? So, again, we're comparing degrees of numerator and denominator. If the degree of the numerator is less than the degree of the denominator, and just, I'm going to say degree of nominator, because there's way too many degree, nom. I always leave out my d's. So just know it's going to happen, and just laugh at me, and know what I'm supposed to be talking about. So, when I look at this problem, what is the degree of the numerator? 2. What is the degree of the denominator? 2. Are there any questions about how we find the degrees of the numerator and denominator? Right, we're just looking at the highest powered exponent. So, this one does not fit this category. Right, the degree of the numerator is not less than the degree of the denominator. So, that is out. But that's case 1. Case 2, if degree of numerator is greater than the degree of the denominator. Then there is no horizontal asymptote. Okay? We'll look in next section at different kinds of asymptotes, like an oblique asymptote. This, when this is the case, you're going to get something that is an oblique asymptote. We're not going to have to find that in this section though. So right now, if there is if the degree of the numerator is greater than the degree of the denominator, then today we're going to write there is no horizontal asymptote. Okay? But again, that doesn't fit my case either. So now there's a third case. That would be if the degree of numerator is equal to the degree of the denominator. Then we have a horizontal asymptote at y equals a over b. Where a and b are the leading coefficients. And sorry, I know my writing on the iPad is awful, but I didn't record this. I didn't record these problems in first period because I wrote them on the board, but then I had like 5 people out first period, so I need to get them written down somewhere. So I used your class as a time to do that. Okay, so we're going to find all asymptotes and wholes of the graphs of each rational function. So when I look at A, 2x over 3x squared plus 1, is this in general form or factored form?
General.
It's currently in general form, right? So I need to see, can I factor it? Because I'm going to need both forms, so this is good. Now let's see if I can factor this. So the numerator, will that factor? No. The denominator, will that factor? No, there is no GCF. There's only one x anyways. So this time the general form and the factored form are actually the same. There is no difference. So let's go through our list. First, we're going to be looking for any wholes. So do I have any common factors in the numerator and denominator? I do not. So that means there are no wholes. Next thing I'm going to look for, vertical asymptotes. The vertical asymptotes happen when the denominator goes to 0. Since nothing factored and made a whole, then that means everything in the denominator is fair game. So when 3x squared plus 1 is 0, I would get a vertical asymptote. So then we'd want to solve this. So I would subtract 1. I would divide by 3. And then I would take a square root of both sides. So what's going to happen? Well, I'm taking the square root of a negative. So what happens when I take a square root of a negative? We get an imaginary. Okay, well, can we graph imaginary vertical asymptotes? No, they do not go on our xy coordinate plane. That means this graph has no vertical asymptotes either. So there are no wholes and there are no vertical asymptotes. Questions about either one of these? You look for what cancels out in the numerator and denominator. Any common factors. It's all over here on the right side too. Any other questions? Okay. And then lastly, we're wanting to look for any horizontal asymptotes. So to find the horizontal asymptotes, we compared the degrees of the numerator and denominator. What's the degree of the numerator? What's the degree? Y'all know how to find the degree? Because you are whispering. It's 1. It's the highest exponent of x. So 1. The degree of the numerator is 1. What is the degree of the denominator? 2. So we have the degree of the denominator is greater than the degree of the numerator. So if the degree of the denominator is... I did it backwards. Since the degree of the denominator is greater than the degree of the numerator, that means I have a horizontal asymptote at y equals 0. Right? We have case 1. The degree of the numerator is less than the degree of the denominator. Then we have a horizontal asymptote at y equals 0. Sorry. So I look at B part. B part, the function is 2x squared over x squared minus 1. So the first thing I want to know, is this in general form or factored form? This is general form, right? I have no parentheses, so it's not factored form. So I want to know, can I write this in factored form? I can. Will the numerator factor? No, there's nothing in the numerator. Will the denominator factor? Yes. It is a difference of perfect squares. So I need to factor that as the difference of perfect squares. So that is x plus 1 times x minus 1. So now I have both. I have the general form of the rational function, and I have the factored form of the rational function. So now I can go through my process. First, I want to look for any holes. So when I look at the factored form, is there anything that cancels in the numerator and denominator? No, there's nothing to cancel. There's nothing that matches. So since nothing cancels, that means there are no holes. Next, find the vertical asymptotes. The vertical asymptotes happen when the denominator is equal to 0. So I would look at the factored form. I have two factors, x plus 1 and x minus 1. So I can look for what makes either one of those things become 0. So I would say, well, x plus 1 equals 0 and x minus 1 equals 0 are both going to give me vertical asymptotes. So solve them. So that's going to give me x equals negative 1 and x equals positive 1. So this graph will have two vertical asymptotes. One at x equals negative 1 and the other at x equals positive 1. Another side note I'm going to make, when you type these in, those are equations of lines. Do you remember how we had the axis of symmetry? And I told you to plug into the formula x equals negative b over 2a, because that was a vertical line, and you were supposed to say x equals. Well, over half of you on the test didn't have x equals. You just had this part, right? It's an equation of a vertical line, so you need x equals. So same thing here. These are vertical asymptotes. They're lines. So the whole thing is your answer. X equals negative 1, x equals 1. You shouldn't write negative 1 and 1. All right, last, we're going to be looking at horizontal asymptotes. I'm just going to abbreviate HA. Okay, so when I'm looking at horizontal asymptotes, I want to look at the general form. So what's the degree of my numerator? 2. What's the degree of the denominator? 2. So my degrees are equal. So I have case number 2. If the degree of the numerator equals the degree of the denominator, then that means we have a horizontal asymptote at y equals a over b, where a and b are the leading coefficients. So what's the leading coefficient of the numerator? 2. Leading coefficient of the denominator? 1. So my horizontal asymptote occurs at y equals 2 over 1, which simplifies to be y equals 2. Again, that's an equation of a line. So you should put that whole thing. Y equals 2 is a horizontal line. Slope of 0. Okay, we finished. Okay, so what was the factored form? We should have gotten 5x squared over x plus 1 times x minus 1 is my factored form because I have a difference of squares. Okay, what were the holes in the graph? There were none. There are no common factors, so there are no holes. Next, we found the vertical asymptotes. So where did the vertical asymptotes occur at? X equals 1 and x equals negative 1. That's correct. We set both factors of the denominator equal to 0 and solve. Any questions so far on holes or vertical asymptotes? Okay, last, horizontal asymptotes, or horizontal asymptote. The degree of the numerator was 2. The degree of the denominator is 2. So the degrees are equal. So we have a horizontal asymptote at y equals the leading coefficients. So that would be 5 over 1, which means that y equals 5 is my horizontal asymptote. Any questions? Any part of that? Okay, look here. Next problem. Find all asymptotes and holes in the graph of f of x equals x squared plus x minus 2 over x squared minus x minus 6. So as you're copying it down, is this in general form or factored form? General form. So I need to factor it to get it in factored form. So this is a trinomial, so you can do the a times c method to get it into factored form. So in the numerator, what multiplies to be 2 added or subtracted is 1. That would be positive 2x and negative 1x. And then in the denominator, what multiplies to be 6 added or subtracted is negative 1. That's going to be negative 3x plus 2x. Any questions about what I've done? A times c, I've got to factor both using the a times c method. So I'm going to factor the numerator by taking a GCF of the first group and the second group. Group out x, that leaves me with x plus 2. GCF of the second parentheses is negative 1. That leaves me with x plus 2. And then in the denominator, when I group, GCF of the first is x. That leaves me with x minus 3. GCF of the second set of parentheses is 2. That leaves me with x minus 3. So both of these worked. So the factored form would be what's in front of the parentheses times the matching parentheses. So I have x minus 1 times x plus 2 over x plus 2 times x minus 3. So now I've got general form and factored form. So first thing I'm going to look for, are there any common factors in the numerator and denominator? X plus 2 is a common factor. So that's the first time we've had one of these. These common factors will cancel out. And so that means there's going to be a hole at x plus 2. So when x is negative 2, I have a hole. So again, I kind of drew for you on the graph what a hole looks like, but a hole is basically just a gap in the graph. So if the graph was supposed to look like this, I erase the point and I put a hole there. So when we write our answer of a hole, we want to write it as an ordered pair because it is just a point. So we know the x value of our hole is at negative 2. And so how do I find the y value? Well, I'm going to plug negative 2 in to the new reduced factored form. So imagine that we canceled x plus 2 on top and bottom. So now I'm going to plug negative 2 into this simplified factored form. So that's negative 2 minus 1, which is negative 3. Negative 2 minus 3, which is negative 5. So the y value would be negative 3 over negative 5, which simplifies to just be 3/5. So there's a hole in my graph at negative 2 3/5. Any questions there? I mean, they're right there. They're in the teacher's lounge. They're coming. So wake up. I send you what? No, you're not. You're doing here. Any questions here? I know. The hole happens when x is negative 2. So then, because the hole is a point, right? Everything else, the asymptotes are lines. So we've been writing x equals and y equals to find asymptotes. But a whole is a point. So I need to find where that point happens. I know it happens when x is negative 2 because they cancel. That's the cancel form. But then I have to plug negative 2 in to the new simplified factored form to find what the y value is supposed to be there, to find the point. The whole is a point where the asymptotes are lines. So you're going to answer it as a point, where the others are answered as lines. Let's go, Bama. Any other questions? Other questions about this whole? Again, that's the first one we've seen with a whole. Okay, next, let's look for the vertical asymptotes. So because we had a common factor, that means this is not part of my asymptote. It's not a vertical asymptote. This gave me a whole. So the only thing that could give me a vertical asymptote would be the factor x minus 3. So I'm going to solve that, which tells me there is a vertical asymptote at x equals 3. So I found the whole. I found the vertical asymptote. Any questions on either one of those? Next, horizontal asymptote. So we need to look back at the general form here. And we are comparing the degree of the numerator and denominator. What's the degree of the numerator? 2. Degree of the denominator? 2. So the degree of the numerator equals the degree of the denominator. So we have a horizontal asymptote at y equals ratio of the leading coefficients. Leading coefficient of the numerator, 1. Leading coefficient of the denominator, 1. So my horizontal asymptote is at y equals 1. But they're good. The factored form of the numerator should have been x plus 5 times x minus 5. The factored form of the denominator should be x times x plus 5. Okay, that should be your factored form for both. Are there any questions for me about either one of those? Okay. Do we have any holes? Yes. We had a common factor in the numerator and denominator that was x plus 5. So that means I have a hole at that common factor, which means when I solve it, the hole is going to happen at negative 5. So to find what the actual point is, we plug negative 5 into the simplified form. So what do we get when we plug negative 5 in? That would be negative 5 minus 5 is negative 10 over negative 5. So negative 10 divided by negative 5 is 2. So my whole happens at negative 5, 2. Questions there? Okay, next we should have found the vertical asymptote. So did I have any more factors in the denominator? I do. X is still in the denominator. That did not cancel out. So when x is 0, I would have a vertical asymptote. So we would set that equal to 0. My vertical asymptote is at x equals 0. So that's the first time we've seen one like that. Right, don't forget, you still set everything in the denominator that doesn't cancel equal to 0. So that would be the x here, equals 0. And then lastly, we want to look for horizontal asymptote. So I'm going to look back at the original general form. The degree of the numerator, 2. The degree of the denominator, 2. So I have a horizontal asymptote at y equals ratio of your leading coefficients, which would be 1 over 1, which means there is a horizontal asymptote at y equals 1.
Hey, wake up.
Okay?
They're in
Yep. Look here. So I've got 3x cubed plus 7x squared plus 2 over negative 2x cubed plus 16. Okay, so this time it asked me to find the domain, vertical asymptotes, and horizontal asymptotes. Well, I still would like to put this in factored form. So let's see, can we factor the numerator?
Yes. No, I mean, it just depends.
Good answer. Okay, if there was a GCF in the numerator, that would be nice. There is a GCF in the denominator, right, that we can factor. In the numerator, there is no GCF. It almost looks like a trinomial, but remember that pattern I showed you where it has to be fourth, second? It doesn't fit that. So I can't do A times C. That won't work either. So the numerator will not factor. That is in factored form. It's ugly, but that's factored form. Look in the denominator. The denominator, will that factor?
Yes.
We did see a GCF, so we can factor that to be negative 2 times x cubed minus 8. And then will that factor?
Yeah. No,
How?
No, it won't. I don't think it will.
You can take the cube root as
Well,
That is one of our special cases we looked at the first week of school. When we went through all of them, that is a difference of cubes. Remember I went through that whole factored worksheet?
Yeah, I learned 34.
Hey, I got it.
Okay, so if I have a cubed minus b cubed, that should be simplified to be a minus b times a squared plus ab plus b squared. So x cubed minus 8 will factor, so I need to factor it again. So that's going to give me, again in the denominator, negative 2 times a minus b. Sorry, I don't know why I put b. I don't know why I put a either. That should be x minus 2 times a squared plus ab plus b squared.
This is the teacher.
So that's the denominator. So I've got 3x cubed plus 7x squared plus 2 over negative 2 times x minus 2 times x squared plus 2x plus 4. So now first, are there any holes? Are there any common factors? Anything I can cancel out in numerator and denominator? So the only way we can have a common factor is if one of these parentheses in the denominator exactly match this, because it wouldn't factor. So it doesn't happen, so there are no common factors. So that means there are no holes. So that's number one. Holes, none. What is happening? There it goes. Next, we want to find the vertical asymptote. So we would have to set each part of the denominator equal to 0. So negative 2 equals 0, that's never going to happen. All right, so we can skip a constant like that out front. All right, so next we have x minus 2 when it's equal to 0. And then we have x squared plus 2x plus 4 when it's equal to 0. So then to solve x minus 2, that means I have a vertical asymptote at x equals 2. Then the other side, well, can I factor that? No. Well, how could I find the roots of a quadratic? I could use the quadratic formula. So I have to plug in x equals negative b plus or minus square root b squared minus 4ac. So let me do that very quickly. That's going to be negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 4. Okay, so what's going to happen underneath that radical? You're going to get imaginary, a negative under the radical. You're going to get imaginary roots. So we can't graph imaginary roots as vertical asymptotes. So that means this part gives me none. Okay, so my only vertical asymptote is at x equals 2. Yep. I mean, we can make it as hard as we want to.
Let's not go.
Well, since I've only got a minute left, you're probably right. I probably won't. Okay? Now, find the horizontal asymptote. So go back to the original. The degree of the numerator, 3. The degree of the denominator, 3. So they agree. So I have a horizontal asymptote at y equals the leading coefficients. 3 over negative 2, or negative 3/2. I'm pretty sure you said 1, 1. To find the domain would be everything from negative infinity until 2, and from 2 to infinity. The only thing that comes out of my domain is anywhere there's a hole or a vertical asymptote.